Hello, so as per the prompt, this problem is dealing with Stokes Theorem, which usually deals with, as this integral is presenting it as a vector field, but technically at different xyz coordinates, you'll have a different field vector pointing at a certain direction with certain strength based on yz, xz, and multiplication products from them. What you were asked is to find the integral over that vector field along each infinitesimal dr. Those two vectors are dot product together over some contoured region or curve C. And that curve is defined by some circle with a radius of 1. And you can tell that from the other side because it would usually be r squared. Square root of 1 is still 1, and then it's up at a height of z equaling 8. So what you have to do is you have to try to rewrite the curve in a form that makes it a little bit easier to work with. So the position vector is some parameter of t is equal to cosine t I hat plus sine t j hat plus 8k hat. The 8k hat is just of respect of that. It's up at z equal 8. The cosine t sine t is for the x and y portions. If the radius were, say, 3, you'd see like a 3 cosine t I hat plus 3 sine t j hat, and the x squared plus y squared would have equaled 9 because 3 squared is 9. So those are the different varying things that you could get. And to make it a circle, you go from 0 to 2 pi, and you include those angles by doing square brackets. I could have done this as a 0 less than or equal to t less than or equal to 2 pi. The display might look different, but the definition is the same. It's from 0 to 2 pi, including them as the values being able to be those values. Now, since it'll be needed in the following steps, you should take the time, or not the time derivative, the derivative in respect to t, your parameter t, of the position vector. So some r prime of t. So derivative of cosine is negative sine, and derivative of sine is cosine. You stick those on their respective vectors. So what ends up having to happen with this problem is we need to rewrite the integral a little bit, because we have a dr dt. We don't have some dr. What we need to do is we need to be able to rewrite our field vector as taking a function of our position as a function of our parameter value t. What you can do is a trick that I learned in high school and was reinforced in college of multiplying by 1 with this dt over dt. And what you can kind of do with it is use it just like regular old fraction that is actually able to be separated and multiplied and distributed differently. You can put the denominator dt to the dr and make the r prime. That should not be a dr dt, dr prime. It should just be r prime of t times dt, because you need to be able to backtrack the steps and go to the prior, and in the form that it's at right now, it wouldn't. So that's supposed to be just a r prime of t, like it is written now. So to input the position vector into the field vector, the components of the position, so the y portion of the y component of position, the z component of position, the x component of position, go everywhere where there was y, z, and x, as shown there. And there you see them being actually put together, and then the net result being mapped. There is some further simplification you could do on the z portion, but you'll see that it is not needed in the next steps, because we have to take the dot product of the field vector dotted to the time derivative vector, as in this portion here, which stems from the original dot product FDR. Whenever you take a dot product, the x components multiply together, added to the y components, multiplied, added together, and then add to the z components added together. And this is why you don't have to simplify, because this z, this complicated looking z, multiplies to a 0. z portion of that vector. So there's nothing to worry about there. And you will end up simplifying to this, which is some scalar value, because the dot products create scalar values. They don't create more vectors, which is nice. We don't want more vectors. So in the following steps, we're now going to simplify this integral. So again, we're going to be inputting our new dot product function. Since we define this parameter of going from 0 to 2 pi for this parameterized function, that's also what the bounds of the integration are going to go to. Of this function here, a little trig trick that you can do is that 40 is the same thing as 48 minus 8. And then you have sine squared, cosine squared. You can use a trig identity and get that down to smaller values. And you can do the simplifications as such, like the following, which you'll then get down to the cosine squared. You have to do a trig identity that cosine squared is 1 plus cosine 2t over 2. You can search up those identities on your own time. And then the following simplifications occur, getting it all the way down where the sine of 4 pi minus sine of 0 is 0, sine of any whole number multiplicative of pi whenever taken of the sine of that. So sine of pi, sine of 2 pi, sine of 3 pi, sine of 4 pi, and so on will make 0. So that's 0 minus 0 times 12, so 0, plus the 8 pi from all the simplification that was done from the above. So the original integral is equal to 8 pi. So that is covering all of Stokes' theorem. If you have any more questions, you can message me on the site. Otherwise, have a good night.